Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. When we think of structural engineering, we picture rigid steel girders, poured concrete, and massive suspension cables. For centuries, civil engineering has relied on brute force, manufacturing dense materials that resist gravity through sheer mass and rigidity. But nature builds under a completely different paradigm. Beneath the forest floor lies a subtle, highly efficient structural network that is currently revolutionizing how architects think about force, tension, and material design: fungal mycelium. Mycelium is the vegetative body of fungi, composed of a vast subterranean labyrinth of branching, thread-like filaments called hyphae. While we usually associate fungi with mushrooms or organic decay, bioengineers and structural physicists have recently uncovered an astonishing physical property hidden within these microscopic threads. When grown under controlled environmental conditions, mycelium forms an interconnected web with extraordinary tensile strength, a biomatrix capable of bearing immense loads while remaining incredibly lightweight. To understand how fungal physics is reshaping modern architecture, we have to zoom in to the cellular level. The walls of fungal hyphae are composed primarily of chitin, the very same polymer found in the resilient exoskeletons of insects and crustaceans, interwoven with glucans and proteins. As hyphae extend, they don't just grow randomly, they optimize their routing based on structural stresses and chemical gradients. When subjected to physical pull or tension, these microthreads align along vectors of force, dynamically reinforcing paths of highest stress. In traditional engineering, suspension and tension bridges rely on high-tensile steel cables anchored to massive concrete piers. While steel is exceptionally strong under tension, it suffers from severe material degradation over time due to oxidation, structural fatigue, and microfracturing. Fungal structures, however, overcome these limits through continuous bioadaptive distribution. When a load is applied to a mycelial network, the force isn't absorbed by a single localized node. Instead, it dissipates dynamically across millions of elastic microscopic filaments. Architects and materials scientists are now harnessing this fungal physics to create unprecedented structural forms: the mycelial tension bridge. By cultivating specialized fungal species on tailored agricultural waste substrates, such as hemp fibers or wood sawdust, engineers can guide the mycelium to grow into precise, high-performance structural geometry. As the fungal hyphae weave through the matrix, they bind the organic fibers into a dense, fibrous composite that excels in both compression and tension. Once the desired structural density and shape are achieved, a heat-curing process dehydrates the mycelium, solidifying its internal geometry and creating an ultralight, non-flammable, and water-resistant biocomposite. But the research doesn't stop with static, cured structures. Advanced experimental projects are exploring living mycelial architecture. In these living tension systems, dormant fungal networks remain embedded within flexible structural membranes. If microcracks form or tension distribution shifts due to heavy loads, controlled moisture and nutrients can reactivate the fungi, allowing the bridge to literally grow, fill its own fractures, and retension itself autonomously. Imagine pedestrian walkways, footbridges, or temporary emergency structures grown on site using locally harvested agricultural waste and tiny fungal spores. Rather than transporting heavy steel beams and carbon-heavy concrete across vast distances, architectural components can be grown directly inside custom tension molds in a matter of weeks. The result is a fully carbon-negative bridge that absorbs more carbon dioxide during its growth phase than it ever emits during its functional lifespan. Furthermore, computational architects are utilizing algorithmic models derived from fungal branching patterns to design optimized structural trusses. By mimicking the topological efficiency of hyphal growth, algorithms can generate light, organic bridge designs that eliminate redundant material without sacrificing structural safety. These fungal-inspired designs resemble delicate, skeletal spiderwebs, yet possess the structural integrity required to span significant gaps. The intersection of biofabrication and structural physics represents a monumental paradigm shift in how humanity inhabits the planet. As urban environments face pressing ecological challenges, the transition from mined, energy-intensive materials to cultivated biophysics is no longer just a futuristic concept, it is an engineering imperative. The humble fungus, long hidden in the soil, is showing us that the strongest structures of tomorrow might not be forged in high-temperature furnaces, but grown quietly in the dark. For more incredible facts like this, don't forget to subscribe and turn on notifications.